All right. So let's talk about sets. So the next unit of material, we're going to talk about sets, and then we're going to talk about functions. And I'll warn you right now, for the material on sets, we're still going to be using the same textbook that I've been using so far, and I will continue to post the pages for the homework assignments directly onto Canvas, as I've been doing. However, when we start to talk about functions a couple of weeks from now, we're going to start to use the textbook that you actually were supposed to purchase for the class. And so when we get into that material, I want you to, I'm not going to post the pages from the textbook onto Canvas. And so if you haven't done so already, definitely make sure that you have the textbook that you were supposed to purchase for the class. Again, you're going to need it in probably 2 weeks from now. We're going to start using it. Anyway, but for the next 5 lectures, we're going to talk about sets. And sets are pretty fundamental to most of the things that we do in mathematics. If you're talking about functions, a function is a map that takes you from one set to another set, and so we need sets for that. If you're talking about something like graphs, if you think of graphs as sets of points and lines, right? Then sets are going to come up there as well. Sets come up when you're talking about probability, which is another topic that we'll cover in this class. So there are a whole bunch of topics we're going to cover in this class that kind of all rely on us having a decent understanding of what sets are. And then besides that, sets are just kind of interesting in their own right. I think they're kind of a fun thing to study. You'll also notice some similarities between sets and formal logic, which we just finished talking about in the previous unit. So anyway, let's get to it. So loosely speaking, we say that a set is a collection of items that we call elements, or sometimes we call them members, right? So we call them elements or members. The homework problems might kind of use those words interchangeably. So just so you know, they sometimes call them members. I use the word elements. So for example, the shoes in your closet at home form a set, right? The set of shoes in your closet. The elements of the set are the shoes themselves, right? But the set of shoes is just, we would consider it a single entity, right? The set of shoes in your closet. We usually use capital letters to denote sets, and when we list the elements of the set, we usually put the list inside a set of curly braces. This is called the roster notation of the set. So, for example, if we define P to be the set of primary colors, then the roster notation for P would be, well, this requires you to have some background information, but maybe you learned at some point in grade school, or if you took like an art class or something, then you may have learned that the primary colors are red, yellow, and blue, right? Those are the primary colors. And so if we're giving the roster notation of the set, then we list those colors. We list those colors in curly braces, as we've done there. Okay. Now we could, and it's useful for us, and you'll see why later on. But we could talk about a set with nothing in it, right? So a set that has nothing in it is denoted by this symbol. It looks like a little O with a slash through it. So a set with nothing in it is denoted by this symbol, and we call it the empty set because it's empty. There's nothing in it. So in other words, the empty set is just a pair of curly braces with nothing inside, right? Okay. If little a is an element of the set A, that means it's a member of the set, right? So if A is an element of the set, then we write this symbol, which looks kind of like a funky looking E. So we say A is an element of A. Or for short, we could say A is in A, right? Little a is in A. So to give you a concrete example, if P is the set of primary colors, then red is an element of P. Or in other words, red is in P. Red is in the set P, right? However, green is not in P, right? Green is not a primary color, so green is not an element of the set P. And so that's how we would say that something is not an element of a set, is that we would write the element symbol and put a slash through it. So let's practice with that a little bit. Okay? So let's say that A is the set 1, 3, 7, and 10. And then let's fill in the following blanks with an element or not an element, right? So for this first one, we have 4 blank A. And so the question is 4 an element of A? And the answer is no, right? 4 is not in A. So we would say 4 is not in A. It's not an element of A. What about 7? Yeah, 7 is in A. So we would say 7 is an element of A. Okay. For part C, we're asking about 2 different numbers, 1 and 3. And we're asking, are those both elements of A? And they are, right? So we say yes, 1 and 3 are both elements of A. 10 is an element of A. Yes, that's an element of A. 5 is not an element of A. So we say it's not an element of A. Okay, so that's how those symbols work. Now, when dealing with set notation, a couple things to keep in mind, right? First of all, the order that the elements are listed in doesn't matter. So the set red, yellow, blue is the same as the set yellow, blue, red. The order doesn't matter. It's still the same set because they have the same elements, okay? And then the other thing is that an element only needs to be listed once in the roster. So the set A, B, C, C, B, D, well, that's just the same as A, B, C, D, right? Repeating the B and repeating the C, that doesn't change the set. These two sets would be considered the same thing in set theory. They would be considered exactly the same. And in fact, usually we like to write our sets without the repeats. So this would be kind of you could kind of think of it like this is simplified, right? This is the simplified version, and we like the simplified version. Okay. Now, when describing a set, it's sometimes useful to use what we call set builder notation. And set builder notation usually gives some kind of rule followed by a colon, right, which is that little dot dot thing, and then followed by an explanation. We read the colon where. So we read the colon as where. So for example, if you're looking at the set of all n squared, where n equals 1, 2, 3, 4, 5, right? So again, we read that the set of all n squared, where n equals 1, 2, 3, 4, or 5. So if I wanted to give, so this is the set builder notation. If I wanted to give the roster notation of this, in other words, if I wanted to just list off the elements of the set, I would say, well, it's any number of the form n squared where n is 1, 2, 3, 4, or 5. So for example, 1 would be an element of the set because if I plug 1 into n, I get 1 squared, which is 1. 2 is not an element of the set, but 4 is, right? If I plug in 2 here, if I plug in 2 there, I get 2 squared, which is 4. So 4 is an element of this set. If I plug in 3, right, 3 squared is 9. If I plug in 4, 4 squared is 16. And if I plug in 5, 5 squared is 25, right? So that would be the roster notation for that set. So this is the roster notation. This is the set builder notation. So this is the set builder. And this is the roster notation. Okay? Let's practice with that a little bit more. I'm going to switch pens because it's a finer tip so I have a little bit more control. But anyway, list the elements of the following sets. So this set is the set of all numbers of the form 1 over n, where n is 3, 4, 5, 6, or 7. So same thing as before. We just take turns plugging in these numbers for n over here. So if I plug in 3, I get 1/3. If I plug in 4, I get 1/4. If I plug in 5, I get 1/5, and so forth. Right? So there's that set. Part B. The set of all numbers of the form n squared, where n equals -2, -1, 0, 1, or 2. Okay. So let's see. If I plug in -2, negative 2 squared. Now be careful. Negative 2 squared is not negative 4. Because if you think about what negative 2 squared should be, it should be negative 2 times negative 2. And a negative 2 times a negative 2 is going to give you a positive 4. Okay? So 4 is in there. If I plug in negative 1 squared is negative 1 times negative 1. That's positive 1. If I plug in 0 squared is 0 times 0, which is just 0. If I plug in 1 squared is 1 times 1, which is 1. And if I plug in 2 squared is 2 times 2, which is 4. Now notice that here I have repeats, right? I've repeated 1 and I've repeated 4. So it's not necessary for me to list the elements of a set more than once. So really this would just be the set 4, 1, and 0, and that's it, right? That would be the set builder, or sorry, the roster notation for this set, right? So these mean the same thing. Part C. So we want numbers of the form x over y, where x is allowed to be 1 or 2, and y is allowed to be 1, 2, or 4. Go ahead and give the video a pause and see if you can write out the roster notation for that set. Okay, so here's my solution. I'm going to do numbers of the form x over y. So I'm going to start by plugging in x equals 1. And so just focusing on x equals 1, right? Now, y can also be 1. So I would get 1 over 1. Or y could be 2. So I could have 1 over 2. Or y could be 4. So I could have 1 over 4. Those are all of the possibilities if x is 1. So now let's focus on if x is 2. If I think about x equals 2, then now I would have 2 over, now y could be 1, so I could have 2 over 1, I could have 2 over 2, and I could have 2 over 4, right? So those are all of the possibilities. But I should probably simplify those numbers, right? 1 divided by 1 is just 1. 1/2 is, of course, 1/2. 1/4 is 1/4. 2 divided by 1 is just 2. 2 divided by 2 is 1. And 2 divided by 4 reduces to 1/2. And now you'll see that I've got some repeats, right? I've listed 1 twice. I've listed 1/2 twice. So really I should have this 1, 1/2, 1/4, and 2, right? And that's that one. Whoa, I went off the page. Sorry. Okay, so hopefully that's making some sense to you. One more. Okay, this time without numbers, because they don't have to be numbers, right? So here's one that doesn't have numbers in it. It says the set of all y, where y is a color on the American flag. Well, what are the colors on the American flag? Red, white, and blue, right? And that would be that one. Okay. We can also work backwards. So instead of being given the set builder notation and being asked for the roster, we could be given the roster and be asked to describe that roster in set builder notation. So if I'm looking at this one, oh wow, -18, -9, 0, 9, 18, 27. What I notice about all of these numbers is that they're divisible by 9, right? They're all multiples of 9. This is 9 times -2. This is 9 times -1, 9 times 0, 9 times 1, 9 times 2, 9 times 3. So they're all 9 times something. So I would write this as the set of all 9 times n, right? 9 times something. But then we have to tell the reader what n is allowed to be. N is allowed to be, well, -2, right? Because -2 times 9 is -18. -1 times 9 is -9. So n can be -2, -1, 0, 1, 2, or 3. So where n equals -2, -1, 0, 1, 2, 3. I should mention that there's more than one way to write these things down in set builder notation. So this, I think, is probably the most obvious one, but you could also have written it something like, I mean, you could have just written it as, you know, the set of all n, where n is -18, -9, 0, 9, 18, and 27. That would also be set builder notation. It's not really useful, because if you're going to write it this way, you might as well just have given the roster, but that would also work. So my point is that there's more than one way to describe a set using set builder notation, but I think this is kind of the most obvious one. Okay? See if you can do part B on your own. Okay, here's my solution. What I notice here is that the numerators are staying 1, 1, 1, 1, but the denominators are increasing 2, 3, 4, 5. And if I think about this first element, 1, I can rewrite 1 as 1 over 1. So the pattern even works for the first element, where it's a 1 in the numerator and then a 1 in the denominator. So the denominators are going 1, 2, 3, 4, 5. So I think the way that I would write this is I would call it 1 over n. And by the way, it doesn't have to be n, it could be any letter. So maybe we would say 1 over k. All right, 1 over k, where k is allowed to be 1 or 2 or 3, and so forth. So I'm just going to say dot, dot, dot. We'll have a better way to describe this kind of thing so that we don't have to use dot, dot, dots in the future. Okay, but that's that one. So here's a better way to describe this kind of set. It's to describe it in terms of sets that we commonly use. So certain sets are used very frequently in mathematics, and so they have special names and symbols. Okay, and so here are some of them. The natural numbers get this symbol, n, where you have this kind of weird double stem in the middle. Your textbook actually doesn't use this symbol, it just uses n, like a normal looking n. But most math textbooks these days will use this symbol, right? So the natural numbers n are the positive whole numbers, right? So n is the set 1, 2, 3, 4, 5, 6, 7, 8, right? On and on and on forever. The whole numbers, w, also get that kind of double stem, right? So the whole numbers w are the natural numbers, right? So it's just the set of natural numbers, but with 0 thrown into the mix. So the whole numbers are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So it's 0 and then all of the positive whole numbers. The integers, they get this letter z. Now, why z? Because it comes from German, and z, I don't speak German, but I would imagine that z is, that the word in German for number or for whole number or something probably starts with a z. So anyway, so integers, we'll call them z, right? It's the set z. Now your book uses the letter I to describe integers, and you know, that probably makes more sense to us English speakers, but I'll tell you right now that that's not the usual symbol for the integers. The usual symbol in mathematics for the integers is the letter z with the double stem, right? But anyway, the integers are the positive and negative whole numbers and 0, right? So it would be the set of all the negative numbers all the way from negative infinity up until -3, -2, -1, and then 0, 1, 2, 3, and then so forth all the way off to positive infinity, right? So those are the integers. So natural numbers are just the positive whole numbers. The whole numbers are the positive whole numbers plus 0. The integers are the negative numbers and the positive, the negative whole numbers and the positive whole numbers and 0. Okay. The next set that's really commonly used is called the rational numbers. The rational numbers get the letter Q. And it's a Q for quotient because the rational numbers are numbers that can be written as fractions, or in other words, they can be written as quotients. So they can be written as in the form a over b, where a and b are both integers, okay, and b is not 0. So that's the set of rational numbers. It's all numbers that can be written as fractions. But it's important that a and b have to be integers, right? So you can't have like the square root of 2 right here, because the square root of 2, if you punch that into your calculator, you'll find that the square root of 2 is like 1.4 something something something, and it goes on and on and on forever. So it's not an integer, right? So in order to be a rational number, you have to be able to, the number has to be able to be written as a ratio of 2 integers, right? So they have to be whole numbers, positive or negative. So a couple things to point out. Any fraction is rational, okay? So any fraction is rational. Of course, when I say fraction, I mean the numerator and denominator have to be whole numbers, okay? But as long as that's the case, then that's going to be a rational number. But there are other rational numbers too, right? Any integer is rational. For example, -3 is a rational number because you can rewrite -3 in the form -3 over 1, right? And -3 and 1 are both integers, and so all of the conditions here are satisfied. -3 and 1 are both integers. -3 over 1 is -3, so -3 is rational. Okay. Many decimals are also rational. Not all decimal numbers are rational, but a lot of them are. For example, 0.75 is a rational number because you can rewrite 0.75 as 3/4. And if you don't believe me, just use your calculator. Do 3/4 and change it into a decimal is 0.75, right? So 0.75 can be rewritten as 3/4, and 3 and 4 are both integers. So 0.75 is rational. Okay. In fact, it takes a little bit of work to find an irrational number. They do exist, but and we'll talk about some. Okay, but anyway, most of the numbers that you're familiar with are probably rational numbers. And then finally, the next biggest set of numbers is the real numbers. The real numbers get the symbol R. And the real numbers are numbers that can be written as decimals. Any number that can be written as a decimal. So basically, any number. Okay? So any number is a real number. The exceptions would be the complex numbers, which you may have heard of from algebra. I don't know if they're going to come into this course at all. But anyway, most of the numbers that you work with on a day-to-day basis are real numbers. Well, all of the numbers are real numbers. Okay, so any decimal number is a real number. Any integer is a real number because, for example, 17 can be rewritten as 17.0, so it has a decimal expansion, right? So 17 is real. Any fraction is a real number because you can always turn a fraction into a decimal just by doing the division, right? This literal 2/5 is literally the same thing as 2 divided by 5. And you can just punch that into your calculator. 2 divided by 5, you get 0.4. So 2/5 has a decimal expansion. So 2/5 is a real number as well. So I listed these sets in this way on purpose because they go from smallest to largest, right? All of the natural numbers are whole numbers. All of the whole numbers are integers. All of the integers are rational numbers, and all of the rational numbers are real numbers. Okay, but the logic only flows in that direction. It doesn't flow in the other direction, right? So not all real numbers are rational. Not all rational numbers are integers. Not all integers are whole numbers, and not all whole numbers are natural numbers. So to help you wrap your brain around that, here's an example, right? So let's see if we can give an example of each of the following. So see if we can give an example of a rational number that's not an integer. Okay? A rational number that's not an integer. So we need a fraction that's not a whole number, right? Lots of examples of that. But one example would be, 2/3. Right? There's a rational. It's a rational number, obviously. It's written as the ratio of two whole numbers, but it's not an integer, right? Because it's not a whole number, right? So we would say 2/3 is a rational number that's not an integer. Another example would be like -1/4, right? Those are both good examples. But something that would not be a good example would be like 7, because 7 is rational, but it's also an integer, so it doesn't satisfy this condition. Another bad example would be something that's not a rational number at all, like pi, right? Pi isn't rational to begin with. Okay, part B. Give an example of a natural number. Well, remember, the natural numbers are the positive whole numbers. So any positive whole number will do the trick. So an example of a natural number would be 1, or 10,347, right? Those are both natural numbers. Part C asks for an example of an integer that is not a natural number. Well, remember, the integers are the positive and negative whole numbers. Well, the positive whole numbers are the natural numbers. So if we're trying to give an example of an integer that's not a natural number, then we need to choose one of these negative numbers, or maybe 0, right? 0 is not a natural number, but it is an integer. So we could say 0, or we could say -1, or we could say -243, right? Those are all integers that are not natural numbers. But as soon as you write down a positive whole number, then that doesn't do the trick, right? Then finally, part D asks for a real number that is not rational. In other words, it's asking for an irrational number. So I mentioned a second ago that the number pi, right? Pi is approximately 3.14. But it's a decimal that goes on and on and on forever, and the decimals don't have a repeating pattern. That makes it an irrational number. So pi would be an irrational number. The square root of 2, which is about 1.41, and it goes on and on forever, is another example of an irrational number. And there are lots of other irrational numbers as well. In fact, a very interesting thing about the crazy sort of universe of numbers that we have available to us is that there are actually more irrational numbers than rational ones. And that's something that we're going to prove, we're going to prove that in the 5th lecture in our series of 5 lectures on set theory. So whatever lecture number that is, I guess lecture 14. But yeah, anyway, so that's that. Here are some more examples of using these common sets. So example 5 here says list 5 elements of the following sets, and here we have the set 3z, where z is an integer, right? Z, this capital Z with the double stem, that's the set of integers. Those are the positive and negative whole numbers. So if I want to list off 5 elements, let's see. Well, first of all, this thing is going to go on and on forever in the negative direction. And then eventually you're going to get to the point where you can plug in, right? You're allowed to plug in any positive or negative whole number here. So if I plug in like -2, I get 3 times -2 is -6. If I plug in -1, 3 times -1 is -3. If I plug in 0, 3 times 0 is 0. If I plug in 1, I get 3. And if I plug in 2, I get 6. So there's 1, 2, 3, 4, 5 elements. But then this is going to keep going on and on and on forever in the positive direction as well. Okay, so notice that something like 2 is not an element of this set. Neither is 7, right? And of course fractions wouldn't be either. Like 2/3 is not in that set. Okay, here's another one. The set 1 over n, where n is a natural number. Natural number, that means the positive whole numbers. So I'm just going to start at the beginning and say, if I plug in 1, I get 1 over 1, which is 1. If I plug in 2, I get 1/2. If I plug in 3, 4, 5, and then this is going to go on and on and on forever. But you see, this gets to the heart of what I was saying on the previous page. Up here when I said Well, we're going to have a better way to describe this set that doesn't require us to use these ellipses, these dot dot dots, right? And here it is, right? We can define this set without having to use this kind of dot dot dot. And the reason that we like to avoid using this when possible, because this is ambiguous, right? We're not 100% sure how the pattern is going to continue, right? But this makes it crystal clear what it is that we're talking about. Anyway, and then we can go the other way around. It says rewrite each of the following sets in set builder notation. Answers are not unique, right? There are lots of different ways that you could write down the answers here. But here we have, so apparently we have something that goes on and on forever in the negative direction until eventually we hit -3, -2, -1, 0, 1, and 2, and then it stops at 2. It doesn't continue after 2. It just stops there. So what I think is that these are all integers. They're all integers, except that they stop at 2. So I'm going to say this is going to be the set of all z, where z is an integer and z is less than or equal to 2. Right? It's got to be less than or equal to 2 because it stops at 2. Right? Here's another example. I've got 0, pi, 2 pi, 3 pi. I guess it would go 4 pi, 6 pi, 7 pi, 8 pi. Or 4 pi, 5 pi. I don't know why I skipped 5. 4 pi, 5 pi, 6 pi, etc. So I think this is like n times pi. But n can start at 0. So I'm going to say n is going to be a whole number. So n is a whole number in this case, right? So n times pi, where n is a whole number. It can be 0, 1, 2, 3, 4, etc. All right. One last topic in this section, and that has to do with the cardinal number of a set. The cardinal number of set is just the number of elements in the set. Okay? We denote the cardinal number of a set with this symbol here, n of a. N stands for number. So number of a is the number of elements in the set A. So a set is finite if its cardinal number is a whole number. Right? So 0, 1, 2, 3, 4, 5. Right? So a whole number. It's finite if it's a whole number. An infinite set is one that is not finite. And we'll talk about infinite sets a little bit later. But you should know that like all of the common sets on the previous page, the natural numbers, the whole numbers, the integers, the rationals, the reals, they're all infinite sets. So you can't just count up the number of elements in them the way that we normally do counting. But we will talk about that later. Okay? So example 7 says, state whether each set is finite or infinite. If it is finite, state its cardinal number. So this first one, P, is the set of all x, where x is a planet in our solar system. Ooh, there's some controversy here. This is definitely a finite set. So it's finite. Its cardinal number, n of p. Well, that depends, right? If you consider Pluto to be a planet, then there are 9 planets in our solar system. If you don't consider Pluto to be a planet, then you would say 8 planets in the solar system. And that's the number that's sort of agreed upon at this moment in history, right? We've decided that Pluto isn't a planet. So, so 8 planets in the solar system. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and not Pluto. Okay, that one's finite. What about the set of natural numbers? Well, I just gave it away, right? That's an infinite set. So we can't give its cardinal number yet. We'll talk about the cardinal number of the natural numbers in lecture 14, I think. Part C says A is the set of all y, where y is a person living in the United States who is not a citizen. That's a finite set, right? It's got a finite number. I have no idea what the cardinal number of it would be, though. N of A. I mean, we definitely don't know for sure how many people there are. So people who live in the United States who are not citizens, this could include undocumented people who live in the United States. It could also include people who are here but who are not citizens but have like a work visa or a travel visa or whatever, right? But person living in the United States who is not a citizen. So this is it's finite, but I don't know its cardinal number. You can maybe look it up. Google it. Okay. Part D. The empty set. Remember this symbol? This is the empty set. This is the set with nothing in it, right? The empty set is the set of just nothing, right? It's just a set of, it's just two curly braces with nothing between them, right? It's the empty set. Well, this is a finite set, right? It's a finite set, and its cardinal number is 0. Because remember, the cardinal number is just the number of elements in the set. If the set is empty, then it has 0 elements in it, right? So the cardinal number of the empty set is just 0. Now contrast that with part E, and I know this is going to confuse some of you, but look, part B is the set made up of the empty set. So the empty set has nothing in it, but B is not the same thing as the empty set, right? B is not the empty set, right? B is the set that has the empty set in it. Okay, so B itself is not empty. There's something inside of B. The thing that's inside of B is the empty set, right? But B is not empty. Okay, B has something inside of it. So B is a finite set. It's kind of trippy because it's like B is a set made up of a set. And that's what's confusing about it, right? But it's a finite set, and its cardinal number is not 0, it's 1. There's one element in B, namely the empty set. Okay, so that one I'm sure was kind of confusing. But you could think of it like part G as well. So part G would be a good one. We'll come back to part F, but look at part G. X is the set composed of the set 1, 2, 3, the set 1, 4, 5, and the set 3. So this is definitely a finite set. And now if you ask yourself, what's its cardinal number? In other words, how many elements are in X? Well, you would be mistaken if you said 1, 2, 3, 4, 5, 6, 7. If you said 7, that's wrong. If you said, oh, well, the 3 repeats, so just get rid of the repeat. The 1 repeats, get rid of that. So say 1, 2, 3, 4. You'd still be wrong, though. Or actually, 1, 2, 3, 4, 5. If you said 5, that's still wrong. Because look, the elements of this set are not the individual numbers. They're the sets, right? So here's one element. It's the set 1, 2, 3. Here's another element. It's the set 1, 4, 5. And here's another element. It's the set 3. So the cardinal number of X would be 3. There are 3 sets inside of X. Okay, so that's the cardinal number of X. Okay, all right. Going back to part F. F is the set of all U, where U is a unicorn that exists in the real world. Okay, that's a good example because look, C is the same thing as the empty set. There are no unicorns that exist in the real world, right? So C would be empty. So C is a finite set. Its cardinal number is 0. There are no unicorns that exist in the real world. So there's nothing in set C. Okay, and that's it.